We'll start today on the second page of the worksheet. Suppose that a friend of yours is holding a meat cleaver and standing atop a ladder at an unknown distance from you. Your friend has placed an apple on the top rung of the ladder and suddenly chops the apple in half. Each piece of the apple shoots out sideways and falls to the ground as shown in the diagram. The trajectory of the apples can be modeled by the function negative x squared plus 20x minus 84, where x is the distance from you in feet and y is the distance above the ground in feet. So this is, the x-axis is in feet and the y-axis is also in feet. So, how far from you did the apples hit the ground? Well, you're not allowed to graph in this one. If I tried to factor that, I'm running into a problem right at the beginning. We have a negative x squared. How would I fix that? Change all the signs to x squared plus 20x minus 84. Is that going to change the graph? Oh, I wasn't paying attention. So how about minus 20x plus 84? There we go. Does that change the graph? It would. What would the new graph look like? It would have the same roots. It would look like that. So the graph changed, but the roots did not. So how would you find where those roots are? You'd factor it. Once you factor it, then you set them equal to 0. And let's say, this isn't right, but let's say that x equals 4 and 10. Okay? The next question asks, how far from you is the bottom of the ladder? How would you figure that out? You would find the average between these 2 points. Okay? Which, in this case, would be 7. Now, again, this is not the right answer, so don't write that down. So, x equals 7 tells me where the middle of the ladder is. Okay? And then 13 asks, how tall is the ladder? How would you figure that out? So if x is 7, how would I figure out the y value? So this is 7 comma something. Plug 7 into which equation? Why not this one? That equation has been altered. And it is kind of a mirror image of the equation we're looking at. But we'd plug 7 in there. So let's say that it was 7 comma 15. The next question asks, how far is it from where you are standing to the top of the ladder? So it wants to know, how far is it from here, from there to there? How would you figure that out? You could use the distance formula, which is essentially Pythagorean theorem. So you have a right triangle. What is the bottom leg of that right triangle? And what is the distance? 7. Well, it's not actually 7, but in the one I made up, it's 7. And then this is 15. So you would do 7 squared plus 15 squared equals c squared and solve for c. Now, when you solve for c, you're going to get positive or negative something, and the negative doesn't make any sense. Only the positive value makes sense in this equation. Okay? So 15 asks, how far is it from where you're standing to where the apples were 7 feet above the ground? So what that's saying is, if I went up here to y equals 7, well, that's kind of a bad example. No, never mind. And I were to draw a line straight across. That line would hit the graph twice. Agreed? Well, if I were to go straight below that, how far is it from where you are to the x value representing where the graph is 7 feet high? Okay? Well, what if I asked, how high is the apple when x equals 9? How would you figure that out? We would plug 9 in for x, right? So if I said 9 feet from where you're standing, how high is the apple? Well, you'd plug in 9 and you'd get some y value. What if I flipped it around and I said, what does x equal when y equals 7? So I go back to my original equation and I write equals y, and instead of y, I would put 7. How would you solve that? So if you have a quadratic that equals 7, what do you need to do in order for it to be solvable? You need it to equal 0. So I subtract 7 and subtract 7, and I'd end up with, that's not working. There we go. I'd end up with negative x squared plus 20x minus 91. Does everybody understand what I've just done? Yeah? Okay. So how does my original parabola differ from that new parabola written in red? It's higher. How much higher? 7 units. So when I take the original parabola and I subtract 7, I get a new parabola that is 7 units lower than the original. So if I grab this parabola and I move it down 7 units, what do you notice? What happened to the roots? And they became closer together. In fact, the roots match up perfectly with these points up here. Does that make sense? So I took this original parabola here, and I set it equal to 7. I want to know, when does this original graph, when is the original graph 7 feet high? There are two x values. It's going to be something just slightly bigger than the left root and something just slightly smaller than the right root. So when I move that 7 over and I create a new quadratic, that quadratic is a parabola that is 7 units lower than the original parabola. And because I pulled it down 7 units, this line here created two intersections, and those intersections transferred down perfectly to be the new roots. So if I solve this quadratic written in red, its roots will tell me where the original parabola was 7 feet high. Do you get that? You do not get that. Where are you confused, Riley? Uh-huh. So let me get some of this stuff. That just isn't working today. So here's my 7-foot line. Okay. I want to know what are the x values for those two intersections, which looks like about here and about here, right? Well, the way to do that using algebra is take the original quadratic and set it equal to 7. So I take, and this really is important. You really need to understand this. So negative x squared plus 20x minus 84, that is this graph, right? Well, I want to know what are the x values. What does x equal when y equals 7? So I set this equal to 7. But I can't solve a quadratic unless this is a 0. If you want to factor or complete the square or use the quadratic formula, it will only work if there's a 0 on the other side. So I subtract 7, negative x squared plus 20x minus 91. So what that does This takes my original parabola and it pulls it down 1, 2, 3, 4, 5, 6, 7. Yeah, that was great, right? So now this new quadratic still has roots, and those roots are in the same place as the intersection that I wanted before. Does that make sense? So all we did was adapted the quadratic we had to create a new one that will answer the question, what x values give y equals 7? Well, there's a problem here. First of all, it's negative. We don't like that. So let's change it again. How would you change it? Change all the signs. So what that would do is flip the parabola upside down. X squared plus 20x. No, I did it again. X squared minus 20x plus 91. Okay. Now, I try to factor it. Are there factors of 91 that add to be 20? No, 91 is prime. So what does that mean? How are we going to find the roots? Either complete the square or use the quadratic formula. Now, I'm going to leave that for you to do. I'm not going to do it for you. But let's say I use the quadratic formula and my answer is 16 plus or minus the square root of 2 over 2. Does that tell me where the apples hit? No. So how would you find the answers? How would you get the decimal if you had this? You would do 16 plus root 2, hit enter, divide 2. 16 minus root 2, hit enter, divide 2. And that will tell you the decimal values. Right there and right there. Okay? So that's part of your assignment today. Look at number 16. How far is it from where you're standing to the middle of the ladder? So we pretended that our ladder was at, what was it, 7, 15. And we found this distance. How would we find the distance to the middle of the ladder? That would be 7, 7.5. And then you'd use the Pythagorean theorem again. But again, don't use those numbers. They're wrong. I purposefully didn't tell you what they were. Okay, turn the page. We need to talk a little physics. Let's suppose that you and all your friends, all 3 of them, went cliff diving. Okay? So you're all standing in line. There you go. So one of you is not very daring. So jumps off the cliff and lands right there. And you and all your friends jump at the same time, and you all jump the same height. But some of you jump further than others. So let's say that's person A, person B jumps like that, person C jumps like that, and then I, who am really daring, jumps like that. If you all jump at the same time, you reach the same height, which person hits the water first? They all hit at the same time. Okay? The rate that you fall due to gravity is not influenced by your horizontal speed. So 2 things are going on here. First of all, you jumped in this direction. And gravity is pulling you in this direction. And because those 2 directions are at right angles from one another, neither of them influence the other. Okay? So everybody hits at the same speed, which is why if you have a gun and you aim it perfectly level and you shoot and the cartridge is ejected perfectly horizontally. Does that make sense? If it shoots up in the air, that's different. But if you shoot and the cartridge is ejected sideways, the bullet and the cartridge will hit the ground at the same time, as long as you're shooting level on a level surface. That makes sense? Okay, so if you shot a gun and dropped a golf ball straight down, the bullet, the cartridge, and the golf ball would all hit the ground at the same time. Okay? Well, knowing that fact, let's suppose that you're standing on the moon. That's you. And you throw a baseball as hard as you can. Ready? Would you agree that that baseball went around the moon a little bit? Yeah? Okay, well, let's say that you throw it a little bit harder. Would you agree that that went around the moon? Well, the speed at which you threw it is slower than the speed at which gravity pulls it down. So there is gravity, there's no air. The moon has gravity. In fact, everything has gravity. Everything. Okay? If you and another person are sitting next to each other in space, holding still, eventually you'll meet. Because everything attracts everything else. But you're just not big enough. So when you are falling, the earth is pulling you down. Well, you're also pulling the earth toward you. But the amount at which the earth moves is so small you can't measure it. So let's say that I throw a baseball and I'm really tough and I throw it so hard that it goes halfway around the moon and then hits. Hey, shh, just because I can't draw the picture. There we go. So, if you were strong enough and you could match this force with the force of gravity, then you could throw the baseball and it would continue to fall until you caught it. If you didn't catch it, what's going to happen? It's going to keep going around and around and around. That is called free fall. Because is it falling? Yes, it is falling. But it's falling using the same force as it's traveling, so it just keeps going around and around. When would it stop? Never. We call that an orbit. So, how do you get a satellite or a spaceship to orbit the Earth? You have to go fast. You have to match your horizontal force with the force of gravity. Well, the closer you are to something, the harder gravity pulls on it. So if you are orbiting really close to a planet, you got to be moving. Okay? The further away from the planet you go, the less speed it takes, I think. I'm not a physics teacher, but that's my guess. So you hear that, well, let's back up. So everything orbiting the Earth is traveling at very high speeds. And if you're not traveling fast enough, then the force of gravity wins and you hit the ground. What if you travel too fast? So if you're traveling too fast, gravity's still going to pull on you, but eventually you would break free. So one of the best ways to speed things up in space is to travel close to planets. It's called the slingshot effect. You get close to the planet, so let's say that this is the moon, and you have a rocket that can only go like 20,000 miles an hour, and you want to speed it up, make it go faster. Well, you aim really close to the moon, and you get close to it, and the moon pulls you down, and you fall, and you speed up, and you're going so fast. That's a good way to change directions. It's a good way to speed up, and we do it all the time. We send things to Mars. We usually slingshot it around the moon. It's just a really good way to change direction and speed up, and it's free. I mean, that doesn't cost anything to use the slingshot effect. So, um, every satellite orbiting the Earth is traveling just as fast as the force of gravity. Well, you can orbit the Earth in any direction. You can orbit north to south, east to west, at some funny angle. Well, most of the satellites that we send up are, I don't know, within 100 and 200 miles of the Earth, and there's still a little bit of air up there. And as they travel around, so say this is the Earth, as they travel around, they hit those molecules of air and they slow down, which is called a decaying orbit. So if you're orbiting close, you have to have a rocket engine attached to you, so every once in a while you can speed up. Because if you don't, then eventually you'll slow down. So you'll slow down and get closer and closer and closer until you crash. The International Space Station is in that zone. And the amount of time somebody can spend on the space station is dictated by how much fuel it can hold. Because if it doesn't burn the rockets every once in a while, it'll slow down and crash into the Earth. Okay? Um, so, that was kind of lengthy. Let's go back to this. So the graph that you're looking at here, it is a graph that measures how high you are versus how long it takes after you jump. So we don't know if this graph is person A, B, C, or D. Because A, B, C, and D follow the exact time versus height graph. Does that make sense? So at 0 seconds, everybody's at the same height. At 3 seconds, everybody is at the same height, or whatever it is. At 5 seconds, everybody is at the same height. And everybody hits the water at the same time. Okay? That's important. So, the equation is negative 16x squared plus 16x plus 60. How high is the cliff? 60 feet. That's the y-intercept. Okay? When are you going to hit the water? I don't know. How would you figure that out? Find the roots. Well, I look at the equation in its current form and I don't like it. It's a negative and it has a 16. Can we change it to make it easier? Divide by negative 4. So divide by negative 4, and I get 4x squared minus 4x minus 15. Okay? Does that change the graph? Yes. It made the graph a lot shorter. So the new graph looks like that. But the roots didn't change. Okay? So, let's say that we solve it. Don't do it, well, not quite yet. Let's say that we solve it and we get x equals 5 and negative 1. What does that negative 1 tell me? If you were to start at water level and somehow shoot up and then back down, those are the two roots. So the negative 1 doesn't make any sense. But the negative 1 will help us find something. So question 19 says, when did you reach your highest point? Well, it's the average of these two roots. So what's halfway between negative 1 and 5? And that would be 2, right? 3 in from either side would be 2. So the maximum occurs at 2 comma something. How would I find that something? And again, these numbers are wrong. I would plug the 2 in where? In for, that's an x, right? So I'm going to plug in x equals 2. Which equation would I use? The original. Why not this one? It's been altered and flipped. And actually, yeah, we flipped it so it would look like that. So I'd plug 2 in there. Let's say I got y equals 70. Number 20 says, how high did you jump? No. You jumped 10 feet. Yeah. So if your maximum is 70 and you started at 60, that means you jumped 10 feet. 21. How long does it take you to rise to your maximum height and fall back to the same level? So it wants to know, how long does it take to go from here to here? Well, if my maximum takes 2 seconds, then it would take 4 seconds to jump, hit max, and get back to the 60-foot level. Okay? Then the last question asks, if your horizontal speed is 22 feet per second, so if your speed in this direction is 22 feet per second, how far did you jump? So if we go back to this picture, let's say that person D was moving at 22 feet per second, and it took 5 seconds to get there. How would you figure out? You just multiply them, and you'd get 55 feet. Well, what if this person was moving at 10 feet per second? 10 times 5 would be 50 feet. Well, my fake route is 5 seconds. That's not what it really is, but that's a fake route. Okay? What if person A was only traveling 1 foot per second? Then it would be 5 feet. They jumped 5 feet. Well, let's go back to let's say that this is the Earth, and there's the equator. If you launch a satellite far enough, now most satellites are in this range here. They're not very far away. But if you put a satellite way over here, we have this imaginary circle around the equator, and you put the satellite in motion in the same direction that the Earth rotates, and if you find the right distance, then this satellite will travel just as fast as the Earth spins. Does that make sense? So if my Earth is rotating like this, and I put a satellite out here, and the Earth rotates at the same rotational speed that the satellite travels, then the satellite will never move in relation to the Earth. I mean, it's still going around at an incredible speed, but its view of the Earth will never change. If you're in this band here, you're going to go around the Earth every couple hours. But if you're way out here, it takes you 24 hours to do one rotation, and the Earth also did one rotation. So if you watch the weather on the news, those satellite pictures always look the same. You're always below the United States, kind of looking up. Do you know what I mean? And that's because that satellite is in a geosynchronous orbit. It's orbiting at the equator at the same speed, well, not really, I mean the same rotation as the Earth, and it never moves. So this satellite here, if you're looking at at America, would never see China, ever, because China's on the other side of the Earth. Okay? So there aren't a lot of satellites up there. Most of them are much, much closer. And a satellite up here wouldn't need to do those burns, at least not very often, if ever, because they're so far away, there's no air out there. There's still a little bit of atmosphere in this band. Okay. Turn to the next page. Lulu has a photograph hanging on her wall that is 8 by 12 centimeters. She wants to replace it with an enlarged version of the same photograph. Her plan is to lengthen both the height and the length of the photograph by the same amount. So the same distance, not a percentage. Not like 10%, but like 6 centimeters. She wants to do it in such a way that the new picture has twice the area of the old picture. Okay? So we don't know how big those question marks are, but we do know a couple things. What do we know? They're the same. So I'm just going to call them x. Whatever they are, they're the same number. What else do we know? So the area of the little one is 96 centimeters squared. What's the area of the big one? Double 96. So little a is 96, and big A would be 192. Does that make sense? Well, what is this length here? X plus 8. What is this length here? And let's do x plus 12. Yeah. Yep. So to calculate big A, we have x plus 8 times x plus 12. Everybody agrees? So that would be x squared. What would that give me? 12x. What would this give me? 12x and 8x make 20x plus 8 times 12 is 96. So this equation represents all possible values of x. Okay? So this is the area equation when x could be any number. But there's only one x that satisfies the equation when it equals 192. So we write equals 192. And that will take all possible x's and bring it down to 1, maybe 2. It's a quadratic, so it could have 2 answers. So how do I find x? Subtract 192. So x squared plus 20x minus 96. So subtract 192, subtract 192, and I get this. Now, let's pretend I solve this, and I get x equals 5 and negative 3. What does that mean? So you can either make the picture 5 centimeters bigger, or does that make any sense? No. If I made it 3 centimeters smaller, would I have an area of 192? No. So the negative version doesn't make any sense. Okay? So you'll find the roots of this. One of them will work and one of them won't work, probably. And then use that information to answer the rest. Okay? You have about 8 minutes left. You can go home and check the answers. There are a couple that I want to talk about on Monday. All right? Good luck.